So let's talk about pH and pOH and how these two relate to each other. So let's start with the basic definitions of acidic, basic, and neutral. When a solution is acidic, it means that it has more hydronium ions than hydroxide ions. However, on the other hand, a basic solution has more hydroxide ions than hydronium. And when a solution is neutral, it has an even balance and equilibrium of hydronium and hydroxide ions. So, let's go over the properties of bases and acids. Acids always taste sour, although wouldn't recommend you testing it at home. It tastes bitter and gross and ugh. And bases, on the other hand, taste bitter, so they both I wouldn't recommend trying. Acids conduct electricity through strong and weak electrolytes. They also form hydrogen gas by reacting with metals. This may change, however, the litmus indicators from blue to red. It varies. And acids also form water and salt by reacting with hydroxides. So the properties of the base have some similarities and some differences, and an example of that will be acids and bases can react with one another to form water and salt. So that's a little nifty idea. And bases can be either a strong or weak electrolyte also. Different from an acid, bases taste bitter and feel slippery. They also change the indicators from red litmus paper to blue. And that's it for y'all, guys. Thank you. Okay, so this is the main part of what you need to know. As well, throughout the video, we are going to go over some more physical examples, such as the phenolphthalein lab and the indicator strip experiment. And so it'll give you a more broader idea of how you can differentiate from an acid and a base. And thanks for joining. So we're going to do the phenolphthalein lab. To your right, we have sodium hydroxide, which we're dropping in right now, and to your left, we have the phenolphthalein. Now, with the phenolphthalein, it's going to turn the solution, or our base, pink. Now, if you remember on the pH scale, pink is what is known for being a base, the most basic solution there is. And we're going to put 3 drops, and there's.
Let's discuss the pH scale. This is just a simplistic pH scale that you may encounter in your everyday life. pH is the measure of how acidic or basic an aqueous solution is. Pure water is considered neutral on the pH scale and is assigned a value of 7. All other liquids are measured in relation to pure water on the pH scale. The lower values are acids. The lower the number, the more acidic, and the higher values are bases. The higher the number, the more basic. For example, lemon juice is usually 2 on the pH scale, while bleach is 13. An acid is a compound that produces hydrogen ions, H+, in water, whereas a base produces hydroxide ions, OH, in water. Acids and bases are everywhere in nature. There are also indicators that exist in nature that tell us qualitatively the pH of a solution. The pigments, which are the cause for cabbage to be red, are one such indicator. Other natural indicators are found in blueberries, beets, and radishes. We can use these natural indicators to tell us the relative pH of other solutions. The stronger acids are at the top of the scale, being 0 to 3.9, and the weaker ones are around the middle, close to being neutral, like milk. Those are from 4 to 6.9. It's the same thing for strong and weak bases. The stronger bases are near the bottom, further away from being neutral, so pHs from 7.1 to 10 are the weaker bases, and bases from about 10.1 to 14 are the stronger ones. In this experiment, we will be measuring the pH of vinegar, the acid, and sodium hydroxide, the base, with universal indicator strips, which are in the middle of the screen. So here we have 3 basic solutions. First going in is the phenolphthalein, which is turning pink. Next is the bromothymol, turning blue. Lastly is the universal indicator, turning turquoise. Now we're testing the pH using strips. As shown, all of these solutions have the same basic pH as a dark blue. Now to the acid. We are mixing phenolphthalein with vinegar and the solution remains clear. Next we mixed bromothymol blue with vinegar, creating a yellow solution. Finally, we mixed the vinegar with universal indicator, causing the solution to turn red. As we test the indicator strips in each solution, we see that these solutions are acidic in pH.
This is the pH measurement of hydronium. It generally just gives you the equations for converting one measurement, like pOH, to another, like hydroxide. So what you do is, to make it a little easier, let's start with pH. If you want to get from OH, which is hydroxide, from a specific pH number, you would have to first find the pOH and from there find the OH. Or you could go the other way and find the H, which is hydronium or hydroxide concentration, hydronium or hydrogen concentration, then go to OH. You can't skip across the middle or take shortcuts. I know, sorry, they don't exist. If you just wanted to find the OH of the H, then it would only be a one-step process. What's listed around the arrows is the mathematical functions you have to do to get from one base to the next. Let's say you wanted to get from pH and you wanted to find out the hydrogen concentration. You just take 10 raised to the negative pH. If you wanted to get from hydrogen concentration to pH, you take the negative log of the hydrogen concentration. If you want to convert between hydrogen ion concentration and hydroxide ion concentration, you take this 1 times 10 to the negative 14th and you divide it by the concentration that you do know. And then to get between these two guys, pOH and OH, it's very similar to these pH and H, except instead of using hydrogen ion concentration, you use hydroxide. In the relationship between pH and pOH, this constant number is 14. The pH plus the pOH of some substance is going to add up to equal 14. Notice that this number keeps coming up. It's a very important number. Just a little background information. Acidity is determined by the concentration of hydronium and hydroxide in a solution, and water contains equal amounts of both of those. Water is actually neutral. pH is used to determine how acidic something is. A low pH equals acidity. The opposite is used for pOH. pOH is used to determine basicity, and a low pH, pOH equals a base. pH is used most often though. Let's do some practice. If the pOH of a solution is 6.3, what is the H? Well, first you would look on the chart and see which formula to use for this transition. To get from pH to hydrogen concentration, you take 10 raised to the negative pH. So all we have to do is say 10 raised to the negative 6.3 and plug it into your calculator, so you get 5.0 times 10 to the negative 7. And this is a hydrogen concentration, so the concentration is used in units of molarity, which is the big M I'm writing right now. Next, if the pOH of a solution is 12.1, what is hydroxide? Again, to get from pOH to hydroxide concentration, you take 10 raised to the negative pOH. So 10 raised to the negative 12.1, a very high pOH, mind you. So when you plug this into the hydroxide concentration, actually it is equal to 7.94 times 10 to the negative 13. This is a very low concentration, which is what we would actually expect of an acid. So, practice number 2. Now, if the hydrogen concentration is 7.5 times 10 to the negative 8th, what is pOH? To get from hydrogen ion to pOH, we have to round the bases just a little bit. First, I'm going to go from hydrogen ion concentration to pH, and from there, I'll go to pOH. You could go the other direction, but we're just going to go this way for time's sake. To get from hydrogen concentration to pH, you take the negative log of the hydrogen ion concentration, and 7.5 times 10 to the negative 8th, and this is going to be equal, oh, by the way, the E, if you don't know already, is just another way of saying 10, so 7.5 times 10, that is 10, and this equals 7.1, and we'll go from pH now to pOH, and you'll take 14 minus 7.1, and your pOH will be 6.9. Now, if the hydroxide concentration is 2.4 times 10 to this 2, what is the pH of the solution? Again, to get from hydroxide concentration to pH, you have to round a couple of bases. You can't do this in one step. We'll go from hydroxide concentration to pOH and then to pH. take the negative log of 2.4 times 10 to the negative 2, and that will give me a pOH of 1.6. Then to get from pOH to pH, you just do 14 minus 1.6, and that gives you a pH of 12.4.